the provided example, there was a mistake made in the initial calculations. When determining the size of an electrical panel, the ampacity of the main breaker, not the individual phase ampacities, is what matters. The provided data indicates phase A total load is 19,276 volt-amperes, phase B total load is 19,085 volt-amperes, and phase C total load is 17,781 volt-amperes. To find the total load, you need to add the loads of all three phases together, which is 19,276 volt-amperes plus 19,085 volt-amperes plus 17,781 volt-amperes, resulting in a total of 56,142 volt-amperes. Next, this total volt-ampere value is divided by the voltage of the system, which in this case is 208 volts. So 56,142 volt-amperes divided by 208 volts equals approximately 269.91 amps. This result is then rounded up to the next whole number, giving us 270 amps. Therefore, the next standard panel size larger than 270 amps would be a 300 amp panel. Regarding the question of why loads are calculated by dividing by 208 volts for panel sizing, but by 120 volts for overcurrent protection device or OCPD sizing in branch circuits, the key difference lies in what each calculation is intended to achieve. The overcurrent protection device, or OCPD, is primarily designed to protect the conductors from overcurrent conditions. The conductors themselves are sized based on the ampacity of the overcurrent protection device protecting them. The ampacity of a conductor is influenced by two main factors: firstly, the voltage of the circuit, and secondly, the temperature rating of the insulation material of the conductor. Generally, the higher the voltage, the lower the required ampacity for a given power level. Similarly, a high temperature rating of the insulation allows for a higher ampacity. In the example, the load calculations are performed to determine the appropriate size of the electrical panel. The panel size must be adequate to handle the total load of all the branch circuits that will be connected to it. The total load is determined by adding up the individual loads of all of the branch circuits connected to the panel. These branch circuits are sized based on the ampacity of the overcurrent protection device that protects them. As mentioned earlier, the ampacity of the overcurrent protection device is determined by the voltage of the circuit and the temperature rating of the conductor's insulation. When sizing a branch circuit, the load is divided by 120 volts because a typical branch circuit is a single-phase circuit operating at 120 volts to ground. However, when sizing a panel that serves multiple branch circuits and operates as a three-phase system, the total load is divided by 208 volts, which represents the line-to-line voltage in a typical three-phase system in North America. To summarize, a 120-volt division is used for single-phase branch circuit calculations, while the 208-volt division is used for three-phase panel sizing calculations. This difference is due to the different voltage characteristics of single-phase and three-phase systems and the distinct purposes of branch circuit and panel sizing calculations. Branch circuit calculations focus on protecting individual circuits, while panel sizing ensures the panel can handle the aggregate load of all connected circuits. Let's elaborate further on the principles behind these calculations. When dealing with electrical circuits, it's essential to understand the relationship between voltage, current, and power. Power, measured in watts or volt-amperes, is the rate at which electrical energy is transferred. Voltage, measured in volts, represents the electrical potential difference that drives the current through the circuit. Current, measured in amperes, is the flow of electrical charge. The relationship between these three quantities is described by Ohm's law and the power formula. Ohm's law states that voltage equals current times resistance, or volts equals amps times ohms. The power formula states that power equals voltage times current, or watts equals volts times amps. These formulas are fundamental to understanding and calculating electrical circuit parameters. In the context of branch circuits, which are typically single-phase 120-volt circuits, the power formula is used to determine the current flowing through the circuit. For example, if a device consumes 1200 watts of power at 120 volts, The current drawn by the device would be 1200 watts divided by 120 volts, which equals 10 amps. This current is used to determine the appropriate size of the overcurrent protection device, such as a circuit breaker or fuse, and the size of the conductors that supply the circuit. The overcurrent protection device is selected to protect the conductors from overheating due to excessive current flow. The conductors are sized to safely carry the expected current without exceeding their ampacity rating. The ampacity rating of a conductor depends on several factors, including the type of conductor material, the size of the conductor, the insulation material, and the ambient temperature. Electrical codes, such as the National Electrical Code, or NEC, specify the allowable ampacities for different types of conductors under various conditions. For example, NEC Table 310.15b16, formerly Table 310.16, provides ampacity ratings for conductors based on their insulation type and temperature rating. When selecting conductors for a branch circuit, it's essential to consult these tables to ensure that the conductors are adequately sized to carry the expected current. In the case of three-phase systems, the calculations are slightly more complex due to the phase relationship between the voltages. In a typical three-phase system, the voltage between any two lines is 208 volts, while the voltage from any line to neutral is 120 volts. The power in a three-phase circuit is calculated using the formula power equals square root of 3 times voltage times current times power factor. The square root of 3 factor accounts for the phase relationship between the voltages in a three-phase system. The power factor is a measure of how effectively the electrical power is being used. A power factor of 1 indicates that the power is being used perfectly efficiently, while a power factor less than 1 indicates that some of the power is being wasted. In the context of panel sizing, the total volt-ampere load of all the branch circuits is added together to determine the total load on the panel. This total load is then divided by the voltage of the system, which is 208 volts for a typical three-phase system, to determine the total current that the panel must be able to handle. The panel is then selected to have an ampacity rating that is greater than or equal to the calculated total current. In addition to the ampacity rating, the panel must also have enough physical space to accommodate all of the circuit breakers or fuses that are needed to protect the branch circuits. The number of spaces required in the panel depends on the number of branch circuits that will be connected to the panel. It's important to note that the calculations described above are simplified examples and that actual electrical design can be more complex. Factors such as voltage drop, conductor dating, and harmonic distortion can all affect the calculations and must be taken into account when designing an electrical system. It's always best to consult with a qualified electrical engineer or electrician to ensure that an electrical system is designed and installed safely and in accordance with all applicable codes and regulations. For example, voltage drop refers to the decrease in voltage that occurs along the length of a conductor due to the resistance of the conductor. Excessive voltage drop can cause equipment to malfunction and can also reduce the efficiency of the electrical system. Conductor dating refers to the reduction in ampacity that is required when conductors are installed in certain conditions, such as when they are bundled together or when they are exposed to high ambient temperatures. Harmonic distortion refers to the presence of harmonic currents and voltages in the electrical system. Harmonic distortion can cause equipment to overheat and can also interfere with the operation of sensitive electronic equipment. By understanding the principles behind these calculations and by consulting with qualified professionals, it's possible to design and install electrical systems that are safe, reliable, and efficient. In summary, the key differences in the calculations arise from firstly the voltage levels involved, 120 volts for single-phase branch circuits versus 208 volts for three-phase systems, and secondly, the purpose of the calculation, protecting individual branch circuits versus ensuring the panel can handle the total load. Always consult relevant electrical codes and qualified professionals for accurate and safe electrical system design and installation.